Hello, my name is Adam Engbring. This project is for the GUI MATLAB file for CE 291 at the University of Wisconsin-Madison. So for my final project, I made a cantilever beam deflection calculator. When subject to 4 different types of loads, I did a concentrated load at the end of the cantilever, concentrated load at the middle of the cantilever beam, which is just L over 2. I also did a case where there's a moment applied at the end of the cantilever beam, and where there is a weight distributed on the cantilever beam. So right now I'll just kind of pull over the cases that I went through. So here we have case 1, or actually I guess in this case we have case 7. So this is beam deflection if there's a concentrated load at the end point. So essentially I made functions for deflection and elastic curve. So deflection allows you to find the maximum deflection at the end of the beam, and elastic curve allows you to find deflection at any point along the beam. So for case 7, the files, you'll find there's a case 7 deflection, a case 7 elastic curve, and that's for a concentrated load at the end of the beam. Case 8 is a concentrated load at distance L over 2. So there's a case 8 deflection and there's a case 8 elastic curve. So you are able to solve for deflection at any point along the cantilever beam as well as the maximum deflection. So case 9 then is a concentrated moment at the end of the cantilever beam. And then again we have maximum deflection and we have deflection at any point along the beam. And finally we have case 10, which is a distributed load W, and then the final 2 functions were case 10 deflection and case 10 elastic curve. So when we open up the GUI file, the GUI file, you'll find that the image that I have to display a cantilever beam displays all 4 types of loads on the same image. However, solving problems, you don't necessarily need to have each specific load. You can say solve just for a case 7 beam, just for a case 8 beam, just for a case 9, just for a case 10. But for simplicity's sake, I combine them all into one. So if there's more than one type of load, say if you have a negative case 7 value where the p-value is say negative 200 kips, and then you have a positive case 8 value, you can find the superposition and then still get the maximum deflections. So I've talked enough. I'm going to go into a little bit on why I chose this problem. If I can find, here it is. All right, so this problem was on my mechanics and materials homework. So the beam deflection at point A, obviously this beam is more than just a cantilever beam, but this end section here is kind of what got me, to think about it, because there's this area acts as cantilever with a concentrated moment load and a distributed load. So we have that, and that's just kind of the problem that got me interested in making this GUI program. So as far as the actual software itself, you can see I have this is the GUI file, and then up top here I have my elastic curve functions. So you'll find that in the script itself, the way that I got this program to work, the units all have to be consistent. Unfortunately, had I had more time to do this project, I would have made it where you could have used English units, metric units, and you could have switched from KSI to PSI for elastic modulus as needed. Obviously, also my moment of inertia is in inches to the 4th, but however that could change depending on the beam. So given more time, I would have added that feature. So here's what you'll find. You'll get 2 values when you plug in your equation. You'll get maximum deflection and deflection at x. So deflection at x is the deflection at any given point on the beam that the user enters. So if the beam is 5 feet long, you can enter x equals 3 to find the deflection at 3 feet, and then max deflection will then spit out the deflection at 5 feet. So this does this by summing up all the cases. Again, this deals with superposition. All right, here we go. So now we are ready to open the GUI file. So I will click run, and now you can see we have the program opened. The window to display the image, all you have to do is click the image cantilever, and now we have an idealized cantilever beam with our 4 cases of concentrated load at the end, concentrated load in the middle, a distributed load, and a moment. So I'll touch on a little quickly here. So a positive p-value indicates a downwards load, a negative p-value indicates an upwards load. A positive m value indicates a moment in this direction where it's going to bend the beam downwards. A negative moment will go bend the beam upwards, and then a positive w will push down, and a negative w will push up. So as you can see over here, we have entry for all the different things. So if I pull up my example problem again, I think I might have closed out of it by accident. Yeah, it looks like I closed out of it by accident. So I don't have the example problem. However, it'll still work the same. So if the concentrated load at the end, 150 kips, there's no case 8, so we're gonna put P2 as 0. The elastic modulus, we'll say it's aluminum 6061, so we'll put it as 29,000, which is a pretty standard elastic modulus value. So moment of inertia, this also is nice because you don't have to necessarily make it just a rectangular beam. It can be any kind of beam as long as you know the moment of inertia. So we'll say the moment of inertia 170 inches to the 4th. The length of the beam, I had mentioned it earlier, I had said 5, so we'll stick with 5. I'd also set an x value of 3, so we will go with 3, and then that will find the maximum deflection at 3 at this point on the beam. We'll say, for simplicity's sake, there's no moment and there's no distributed load either. So if we click solve it, we get the maximum deflection. The deflection at the end is negative 2.19 inches, and the deflection at x equals 3. So at this point here, the deflection is negative 0.94 inches. So obviously this is a very handy calculator. Like I had mentioned earlier, it would be more helpful if you could convert the units back and forth as needed. Say, you're given obviously feet is a pretty convenient unit, but if you're given it in inches, the user has to go convert it himself. It might be convenient to have a pop-down menu to change this to inches or a different English unit, as well as some of these other values, because assuming someone using this program is well versed in mechanics and materials, which necessarily isn't the case, and they might not know a conversion from PSI to KSI, and if the question gives the elastic modulus in PSI, they have to manually do it themselves. So, and then obviously that correlates into kips and kips per foot here as well. So I'm just gonna go ahead and enter some more values in here, just so you know that it is functioning correctly as it should be. So now we have 10 at the center, so these values should go up slightly, probably not too much. Yeah, so they went up. So negative 2.2363 and negative 0.97. So that one obviously is working. And if we put in a moment of 50 kips per foot, 2.4 and negative 1.049. So they do go up as well still there. And if we do a distributed load, we'll say 6.7 because that's what was on the homework problem I showed at the beginning of this video. We'll see 2.6. And there we go. So, and then obviously, you can change, if you got a bigger cross-sectional beam, you can change it. The values, they'll shrink accordingly. They'll shrink accordingly as needed. So this is a very handy tool. I've used it to study for mechanics and materials. Another interesting application that this could have been used for is making an actual beam deflection calculator that deals with the rest of the cases. So I'll pull this screen back up. It would have been kind of cool to have a calculator that does deflection for this, because that's more of the types of problem that a student or professor would need. So had given more time, I would have tried to incorporate that in as well. However, I figured for the time frame on this project, my cantilever beam deflection more than suffices. need a good grade on this to boost up my grade in the class. So going back into MATLAB here. So yeah, so we're back to this. So and then you can put in the values. So if you put in a negative 150 value, you can see that the deflection is now going upwards because P is acting upwards. If you put in a negative value for moment, you're all the same. So and now going back into this a little bit, just so I can kind of talk about my code and how I got everything to work, I will put my my beam deflection up next to it. I do have so my computer at home has 4 monitors, so when I'm scrolling them off the screen here, I'm scrolling them onto a different monitor, so it's going to kind of just half sit there. So yeah, I can't actually even work in MATLAB without it being open, so I will do this. I can't make the beam deflection calculator any bigger, but you'll get the gist of it. So in order to convert the user entry boxes here to text, I used this formula here, which I just obviously found online, as there's no other better way for me to do it. My I value here I had put in inches to the 4th, but in order for the units to be consistent, you have to convert it to feet. So I did I over 144 to get it into feet squared. And then, that just deals with the entry of all those text boxes. As far as the maximum deflection is the case 8, case 7, case 9, case 10, max deflection, and the deflection at X is the elastic curve deflections of all the user input variables. So P is, concentrated load for case 7, P2, concentrated load for case 8, E is elastic modulus, I, moment of inertia, L is distance, length of the beam, M is moment, W is distributed load, and X is the elastic curve value. So that about sums up my project. Like I said, given more time, I would have made some tweaks to it to make it a little more, practical past just this class, and so that people could use it in the future. However, I believe this project does a good job in representing my gained knowledge of MATLAB, not only using the GUI system, but using functions, using variables, and integrating it into a successful program. I think this project really does demonstrate my learning very well. I'm hoping to come out of this class with a B, and I feel like this project definitely will put me up to that mark. My midterm scores have been pretty consistent. I'm hoping this project will put me into the spot where I need to be. I do apologize for the clicking in the video. My keyboard was really loud. I wasn't entirely sure how to drown out the sound, and my movie making skills aren't super good, so I couldn't really edit the sound out as I wanted to. But you get the point. So I hope you have fun using my calculator. I'm exploring with it a little bit. There's no exit button. I had some issues getting that to work. So if you want to exit the program, all you gotta do is exit out on the the top right hand corner. So I figured it wasn't too big of a deal. But like I said, if I was given more time, I would have made some changes with the units. But I had a good time in 291, and I look forward to taking fluid mechanics with you either next fall or next spring.